Okay, I just want to go over calculating errors with you to make sure that you're confident when you're calculating errors in your exams. So before we do that, I just want to quickly look at tabulating data. So taken from the AQA, it's important to keep a record of data while carrying out practical work. Obviously, tables should have clear headings with units indicated using a / before the unit. Okay, so obviously here we've got a / so here it's really important. A lot of students not looking if it says milliamps, for example. Lots of marks are lost because they'd be out by a factor of 1,000. So it's important that you're really careful and you look at this. Now, or you can use a solidus, a / or you can have brackets. So brackets are acceptable normally. And if you look here, all of the data is to the same number of decimal places, which we'll look at now. So here, significant figures. So data should be written in tables to the same number of significant figures, and it should be determined by the resolution of the device being used to measure the data or the uncertainty in the measurement. For example, a length of string measured to be 60 centimeters using a ruler with a millimeter scale should be recorded as 600 millimeters or 60.0 centimeters. So when you're doing this, it tells the reader that, so if you say here it says not just 60 centimeters. So as the reader, when I read 60.0 centimeters, it tells me that they have done that to a resolution of a millimeter. So I know how accurate the reading was taken. However, if it says 60 centimeters, I would assume they've used a primary school ruler with no millimeter scale on it, and that's the level of precision that they've gone to. So it's important that you show the number of decimal places. Similarly, a resistor quoted by manufacturers 56 kiloohms with a 5% tolerance. The tolerance should not be recorded as 56 kiloohms, okay? Because your 5% tolerance would suggest that this was accurate, and of course it's not, because we've got 56% of 5% of 56 kiloohms would mean that we couldn't give a level of precision which would give us this next decimal place here. Okay. Now then, sometimes it says here there is confusion of the number of significant figures when readings cross multiples of 10. So here we can see we've gone up from 0.99 to 1.00. Okay, so this is an area of confusion for a lot of people. So changing the number of decimal places across power of 10 retains the number of significant figures but changes the accuracy. The same number of decimal places should therefore generally be used. Okay, so here where we've got a certain number of decimal places, so we can see we've got 2 decimal places in a table, and here we've got 1 decimal place in the table, but suddenly our number of significant figures here, we've got 2 significant figures, and then suddenly it's changing here, okay, and here. But that's okay because it's saying we're using 2 decimal places, so keep it the same even though we've crossed a multiple of 10. And the same is true here. We're on 1 decimal place, 3 significant figures, but then suddenly we cross this 10 boundary here, but we're staying to 1 decimal place, which means that we've suddenly got additional significant figures. We could have additional significant figures here, but then that's acceptable. Okay. Now then, I've mentioned this in an earlier video, but there are different sources of uncertainties, and it's essential that the students know where they might arise. So, for example, there are things to consider such as the resolution of the instruments, the tolerance of the instruments, the judgments made by the experimenter, which is a massive source of errors, the procedure you've adopted, for example, repeat readings or whatever, and the size of the increments available, so the size of drops in a pipette or whatever. Now, when you do this, it's really important, because you're going to be going to calculate errors in a moment, that you are clear between readings and measurements, because this is what they're going to be looking at. Okay. Now then, with a reading, that's where you'd only make 1 judgment. So, for example, a thermometer. In a thermometer, we assume that you only take the reading of where the liquid is up to, and that we can assume that there is no zero error, that reading is accurate, and that the zero error, that there is no zero error. a top pan balance is the same, measuring cylinders are the same. You're assuming that the manufacturer has calibrated it accurately, so you only have to take one reading. Conversely, there are things such as rulers, vernier calipers, micrometers, protractors, stopwatches, any analog meter. You're taking a ruler at a measurement at the beginning, and you're taking a measurement at the end. Now, so it's really important because you've got two errors, one at the beginning and one at the end for all measurements. Now, as you'll see in a moment when I talk, I'll come back to this. We often find, though, just because of number of significant figures and so on, we often find that whilst a reading should give us a more precise value, we often find that it doesn't, because we have to quote to a certain number of significant figures anyway. We often find that the measurement value, which is less precise than the reading because there's two errors in it, we often find that they give the same reading anyway because of the number of significant figures. So let me show you an example. So if we look here, we've got an object and we've got it on a ruler. Now we can see here the object is aligned with the ruler here and the object is aligned with the ruler here. Now then, but there's a window. There's a window of where we've got an uncertainty in our reading. So we can see here it says, we're measuring length, two uncertainties must be included. The uncertainty of the placement of the zero of the ruler and the uncertainty of the point of the measurement is taken from. Both ends of the ruler have a plus or minus 0.5 scale division. The measurement will have an uncertainty of plus or minus 1. So what we can see here then is we've got this scale going up. So say it's in, I don't know, centimetres. So this should be 0 centimetres, 1, 2, 3, 4, 5, 6, 7, 8 centimetres. But we can see when something is there, all we can say is it could be plus or minus half a division. That's the level of precision we're aware of. So we know there's plus or minus, plus or minus half a scale division. In this case, we're saying it's a centimetre, and that's there. But we've got the same here. So whatever reading we give, we can see that. Now we're saying this is 1, 2, 3, 4, 5, 6, 7, 8. However, if we were off by half a scale here and half a scale here, if they were both, if it was the worst case scenario, then it would give us a reading of 9 centimetres or 7 centimetres if both of the errors went in the wrong direction. And therefore, we have to add them together. So we know then that the reading, in this case, would be 8 plus or minus 1 centimetre, because we add the two 0.5s because we cannot be accurate to greater than plus or minus 1 centimetre or 1 division in this case. That's the example for a measurement, because in a measurement we have 1 there and 1 there. In a reading we only have 1 of them. However, in a reading, what you're often doing is, if you've got a reading, for example, and it says 36.1 degrees C. So your level of precision then, you could say, well, that's 36.1. This is when it's a reading now, not a measurement. Plus or minus 0.5 degrees C. But I'm taking this, my apologies, I've taken that to the wrong level, so I'll just do that part again. My apologies. If we had on a reading, if we had 36.1 degrees C, we'd be tempted to say this must be plus or minus. Now, the level of the resolution of our instrument is 0.1 degrees C. So we know then it would be 0.05 degrees C. But our instrument, our readings, we're only quoting to 1 decimal place because that's the precision, the resolution, if you like, of our instrument. So even though our uncertainty is only half that, even though it's a reading, I can still only say that this is 36.1 plus or minus 0.1 degrees C, despite the fact that it's a reading, because my number of decimal places, because I cannot give a value, a level of precision which is smaller than the resolution of my instrument. So therefore, although this is a reading, it's still giving me the same level of precision as a measurement would give. Now then, here, if we look at this is just a simple example of Hooke's law. We've got a starting point here, a finishing point here. We're looking at the extension delta L of a spring, and we can see then that we've got an uncertainty here. If this is in millimeters, we've got an uncertainty here of 0.5 millimeter. We've got an uncertainty here of 0.5 millimeter. So we add those two uncertainties together to give us plus or minus 1 millimeter, assuming this is obviously a millimeter scale. So it's important that we understand the difference between readings and measurements, and that we understand that in some things there are two required judgments, and in readings there's only one, and that enables you to understand where the uncertainties come from. Now, another way uncertainties are calculated. So one thing would be, you could be given an answer, you would just be told that the length of something is 7.7 millimeters. And if somebody told me the length of something was 7.7 millimeters, because I understand this process, I would know then that actually that's 7.7 millimeters plus or minus 0.1 millimeters, because I understand that half of my resolution at each end means I've got plus or minus the resolution of the instrument, so that would be my uncertainty. Now, here, this is where we've got repeated readings. So when you have repeat readings, there's another way to calculate uncertainty. So where we've got random errors, we might repeat an experiment several times to eradicate or trying to reduce the impact of those random errors. So we do repeat readings in many experiments, as you've done when you've done your required practicals. And here you can see there's another way to calculate uncertainties, and that is plus or minus half the range. So here we've got 4 readings, and we just find the highest and the lowest. So the highest was this one, and the smallest was this one. So that gave us a range of 1.32 minus 1.22. Now that equals 0.1 meters. So that there is the range. So when we want to work out the uncertainty, it would be the mean plus or minus half of the range. So in this case, we can see here, the mean is 1.26, gained by adding the 4 values together and divided by 4, and then plus or minus half of the range. This was the range, and it's plus or minus half of that. We could then go on to work out that that's the absolute uncertainty. We could then go on to work out the percentage uncertainty later, which would be needed for certain calculations, and if we were going to multiply uncertainties and so on. Now here this goes over, and you've seen this before, but this, and I've just gone over it. We could then convert that into a percentage uncertainty by doing by calculating the uncertainty as a percentage of the mean value. So this is an example which you can read if you choose to. But if we go back to this example here, our percentage uncertainty here would simply be 0.05, because that's our uncertainty in this reading, divided by 1.26 times 100, and that will give us our percentage error, as opposed to our absolute uncertainty, which is here. This would give us a percentage. And if you look at this example here, that's what this is saying here. So it's saying the exact values for the mean are whatever, the uncertainty is whatever. Now, this could be quoted as such or recorded as this, given that there's a wide range in only 4 readings and the simplistic nature of the analysis, then giving the percentage uncertainty as 5% or 6% would be fine. Okay, so in that example here, they're showing us that there's some flexibility because of the nature of that experiment. All right. Now, another thing we have to do in physics, which is very straightforward, is sometimes you'll have to plot graphs. And graphs can have error bars in them, and it's important that you're able to look at error bars, and when you're looking at error bars, you need to be able to draw a graph, the line of best fit, and look at the the worst possible gradient that you could get and still lie within your error bars, because the truth does lie within those error bars. So it's important that you can show what will be the most likely gradients, the best gradients if you like, and also the worst. Now, we don't need to worry so much in physics about formal confidence limits. We just need to understand that we can plot the data at the mean value, calculate the range of the data, ignoring any anomalies, and add error bars. And the error bars will just simply show whatever plus or minus half of the range. So if the answer was 5 plus or minus 0.5, so then your error bar, you plot your point, and you'd have a 5, and it would go up to plus or minus 0.5 either side. Now, this is very important. When you're looking at a graph and you need to calculate the uncertainty in the gradient, because the gradient will be used as part of y equals mx plus c, they're going to ask you to determine constants or determine all sorts of things from graphs. You're going to be using the y-intercept, and it's really important that you're going to determine the gradient, and sometimes you'll be expected to determine the uncertainty in that gradient. And when that's asked, you need to draw 2 lines on the graph. One should be the best line you possibly can, the line of best fit, the line that looks like it would go through the most points in the best possible way. But the second line should be the steepest or the shallowest line that is possible whilst remaining within those limits, those error bars. Now, we then find the percentage uncertainty in that as the best gradient minus the worst gradient. Now, here, they've got modulus bars around them, and all that means is we're after a magnitude here, a positive value. So basically it's the difference between the worst gradient and the best gradient. So the worst gradient might be bigger or it might be smaller, but it's the difference, positive value, that's the difference, the magnitude of the difference between the best gradient and the worst gradient. Divide that by the best gradient, the perfect one, times by 100%, and that will give you the percentage uncertainty in the gradient of a graph. So if, for example, if you've got a graph here and the best line is like that, within your, obviously you've got points here and you've got little error bars all along the graph, and you're saying, well, that's my graph's not very good, sorry. And you're saying, well, that's the best possible fit. However, there are other graphs which could go from the top of this one all the way through there. There are others which could go all the way down there. Now, you need to determine which of these is the worst, and the worst will always be the most different, if you like, from the best. And it's the difference between those two divided by the best will give you the percentage uncertainty in the gradient. So here's a much better example than mine. This one's provided by the AQA. So here we've got a scattering of readings here, and these are, although they haven't drawn error bars on, it's been sort of determined that these are acceptable graphs you could draw through this data. However, the best gradient there is the solid blue line. The shallowest possible gradient is the red one, and the steepest possible gradient would be the dotted blue one. So you just look at the two values for these and see which one is the most different from the best line, and then obviously it would be the difference between those two values divided by the best times 100 would give you the percentage uncertainty. Now, it's essential that you can confidently combine uncertainties. Now, it's very, very easy when you're dealing with, say, measurement. When you're dealing with something like measurement, so you're measuring the length of something and the length of something else. Now, they're both in the same unit, it's fine. You can add the absolute uncertainties. So, for example, if the uncertainty, so we're adding, in this case, it seems that we're looking at U and V. So, U is 5 centimetres, V is 7.2 centimetres. And we're subtracting them or adding them. It wouldn't make any difference when you're either adding or subtracting, but it would matter that they're all got exactly the same units. In this case, it's just 7.2 take away 5 is 2.2. However, we have to add our absolute uncertainties, which again are in the same units. So in this case, it would be 2.2 plus or minus 0.2 centimetres, because the rule is when we're adding or subtracting, we just simply add the absolute uncertainties, okay? So absolute uncertainties, a very, very simple concept there. However, if we're going to multiply uncertainties, or we're going to multiply values, so in this case A equals B times C, so we can see here we've got V and I. We seem to be multiplying V and I, so we must be calculating, yeah, there we go, we're calculating power. So in this case here, we have to work out each one as a percentage uncertainty first. So in this case, we would say 0.1 divided by 15.2 times 100 gives us 0.7%. In the current, 0.01 divided by 0.51 gives us an uncertainty of 1.96%. Now, we've now got them in percentage terms, so now we can add them together to give an uncertainty of 2.66%. Now, the value of the power is simply 15.2 times 0.51, which gives us 7.75 watts. So the answer would be 7.75 watts plus or minus 2.66%. But if we were asked to give that as an absolute uncertainty, we would then have to work out what 2.66% of 7.75 is, which in this case it's 0.21 watts. And then we could give our answer as an absolute uncertainty, which would be 7.75 plus or minus 0.21 watts. And we look, and the number of decimal places is acceptable there. Okay. Dividing is exactly the same. So when we're dividing values, it's exactly the same as when we're multiplying, because effectively it's the same thing. So again, we just add the percentage uncertainties, just like we did last time. So when we're multiplying or when we're dividing, we just add the percentage uncertainties, and it has to be converted into a percentage first. And the last one, which again is effectively just multiplying again, but this is a power rule. So if you've got A equals B to the power of C, all you've got is, so if this was A equals B squared, it's just B times B, or if it's A equals B cubed, it's B times B times B. It would just be 3 lots of the uncertainty in B. So, because you're just adding them. But each time again, you're doing this, we've got to make sure that we do this as a percentage. So the example here is the radius of a circle is this, and the uncertainty is that. Now we know the uncertainty of a circle, the radius of a circle is 2 pi r. My apologies, what we're doing the area, it's pi r squared. So if we're looking at the area, pi r squared, now there's no error in pi, there's just an error in r. So you've got an error in r times by an error in r. So there's 2 of them. Now this is because it's b squared here. So this is where the c is here. We're putting it down as 2. So it doesn't matter. If it was cubed, it would be 3 of them, and so on. So all we're doing is we're working out 0.1 out of 6 gives us a percentage uncertainty of 1.6. However, we've got 2 of them, so we just times by 2 to give it an uncertainty, a percentage uncertainty of 3.2%. And again, if it was 4/3 pi r cubed for the volume of the sphere, we would be timesing it by 3 instead of 2. Okay, so that's all we do. We're just multiplying the percentage uncertainty by the power. Then here you could work out the area of the circle, which in this case, using 6 centimetres, the area comes out to be 113.1 centimetres squared. We know our percentage uncertainty is 3.2%, so we could write it as 113.1 centimetres squared plus or minus 3.2%. Or we could use the 3.2% and do 3.2% of 113, which would instead give us this, which is an absolute uncertainty. So it just depends how we're asked to present the information at the end. Okay, so there's just another way of doing it. We're not going to be asked to calculate uncertainties in trigonometric or logarithmic functions. And percentage uncertainties, it's worth noting that they don't have units. Okay, so percentage uncertainties do not have units at the end, because it's a percentage of whatever the value is. One of the last points here is just measuring gradients. When we measure gradients, it's important that the line of best fit here, you can see, has an equal number of points on both sides. It's not too wide, it's as thin as possible actually. And we can see points clearly underneath. The gradient triangle has been drawn, so the hypotenuse includes more than half of the line. It needs to be as big as you possibly can make it. It starts and ends on points with the line of best fit across the grid, so it's very easy to read. You are going to have to rearrange possibly quite a complex equation in the form of y equals mx plus c in order to determine something. So you do not want to have errors on your gradient, because when it's being constructed by the examiner will have written in a tolerance, and there's an expectation you will be within that tolerance. So it's very important you draw as big a triangle as possible, and that you try and make your lives as easy as you can by trying to make up any gradients that you line up nicely with points so it's easy to read. And lastly then, so here, this is something that you're going to have to do. You will have to rearrange an equation in the form of y equals mx plus c, given that you'll have something on this axis and something obviously on this axis, which is x, the x-axis. Now, obviously, you all know y equals mx plus c. You know m is the gradient, and you know c is the y-intercept. You are going to have to draw your graphs as accurately as possible so that you can determine whatever these constants are within the tolerance which is expected. I hope that was useful. If you have any questions, then you'll have to let me know. Then you can message me. Okay, thank you.